both of these papers noted an inconsistency in the rotation curves of observed dwarf galaxies and their analogs in dissipationless lambda CDM simulations. The other one of these inconsistencies is the too big to fail problem, first recognized in Boylan-Kolchin et al. 2011. And this was an incompatibility between the largest satellites observed for the Milky Way and those found in lambda CDM simulations. So dwarf galaxies of this size are also incredibly interesting because these are the faintest, this is around the range of the faintest observed isolated dwarf galaxies. So if you're looking for an isolated, dark matter dominated system to compare to, your simulations compare them to observation, this is the scale you want to be simulating. This is the scale you want to be looking at because you'll have a good observational analog. And then finally, the dwarf galaxies at this scale are thought to be at the threshold where reionization can have a dominant role or an influencing role in the galaxy formation of these dwarfs. And so they can be very sensitive to reionization, and they can be a strong tool for reionization. So I just want to go into the details of my simulations. Those were the motivations why I would want to simulate dwarfs of this size. And so I've simulated 12 isolated dwarfs with a virial mass of 10 to the 10 solar masses. And this was run with the Gizmo code and run in the meshless finite mass hydrodynamical implementation. This was run with the fire feedback scheme to simulate all of the baryonic feedback and stellar formation, etc. And these were all selected from 35 megaparsec boxes, 35 megaparsecs on each side. And when I say isolated, I just want to note that there are no larger halos within 5 virial radii of these dwarfs. So these are off on their own. They're isolated. They're not going to be influenced by any larger halos. And I also wanted to note the smoothing lengths and particle masses for these simulations just to show that these are some of the highest resolution simulations of isolated dwarf galaxies at this time, and that these scales are, or this resolution is necessary not only to properly simulate the feedback, the fire feedback, but at the same time to resolve the central parts of these dwarfs which we're so interested in. So for the first set of results from the simulation, I wanted to focus on the mass assembly history, or the virial mass throughout time. In gray here we have my simulations, and in the black dashed line we have the mean assembly history for halos of 10 to the 10 solar masses pulled from the Millennium 2 simulations. This is the mean assembly history from all the halos in the Millennium 2 simulation, and this was presented in Fakori et al. 2010. And so I want to note that at z of 0, we have a very tight, narrow range of virial masses all focused around 10 to the 10 solar masses. But we have a healthy spread of assembly histories at early assembly times, roughly 3 gigayears into these simulations. And so we have a fair amount above and below what would be expected from the Millennium 2 simulations. And just to take a quick glance at the solar masses or the stellar masses that we're producing in these simulations, I just want to note that, once again, we have a narrow range of halo masses, but we have almost 2 orders of magnitude change in the amount of stellar mass produced in these halos. So if we combine those two, the mass assembly history and the stellar mass, here it's colored by the stellar mass at z of 0. We notice that there's not much of a strong correlation between the two at z of 0. But if we focus on earlier times, on these early assembly times, we notice that the halos that are assembling more mass earlier correspond to halos that are going to have more stars at z of 0. And to just underline this fact, I've looked at the maximum circular velocity through time. And this is a tracer of the central potential of these galaxies. We can see that, once again, this parameter, this property, is set at this early assembly time and remains constant for the most part throughout these simulations, albeit for a couple of major mergers that some of my dwarfs experience. And we can notice that we have an increasing Vmax with increasing stellar mass, and that seems to hold for most of these simulations. Okay, so yeah, and so these are all interesting results, the global properties of my simulations, but it's only interesting if we can frame this, compare this to observation. Do these replicate what we observe? And so here, I've just got the half-light radius to the stellar mass, and in black are isolated dwarf galaxies, and in gray are satellite dwarf galaxies from Kirby et al. 2013, 2014, and in blue are my simulations. So we have a nice fit here to the data. And also, if we look at the mass-to-light ratio, once again compared to stellar mass, we see that my halos, or my galaxies, are doing a realistic job at reproducing these observable trends. Namely, that we're seeing in fainter galaxies that these are more increasingly dark matter dominated. Finally, I just wanted to look at the actual star formation histories for my halos. And here we have a plot from Skillman et al. 2014, and we see a nice spread of star formation histories with early to late star formation. And if I compare those directly beside my simulated star formation histories, also just to note, these are normalized to 1 at z of 0. We see a very similar spread, so these are qualitatively similar between the two, which is encouraging. So now that I've compared to the global properties of observation, I'd really like to delve into the centers of these halos, namely the radial density profiles of these halos. Specifically, if we look here in black, we have the hydrodynamical simulations. In the gray dashed line, we have the dark matter only simulations, the corresponding dark matter only simulations. And then in the black dotted line, we have the half-light radius. Now, I've also noted the stellar mass of these halos at the top here. And so I really want to stress that these all have roughly the same halo mass, and that we are not finding cores for halos below that are galaxies that have less than 10 to the 6 solar masses. And so this is a result that has been seen in the literature before, so this is encouraging. But once we get beyond this threshold, this 10 to the 6 solar masses, we see that increasing stellar mass corresponds with a decreasing central density, a greater reduction in that central density. And so now if I were to put all of the halos that I've simulated into one plot, now I have the x-axis scaled as the half-light radius, by the half-light radius, and the ratio of the density in the hydro run to the density in the dark matter only run. So we would expect, and this is once again colored by the stellar mass at z of 0, we see that the bluer lines, which correspond to the lower star formers, have roughly a ratio of nearly 1. So there we see a core in both simulations, the dark matter only and the hydro. But as we increase m star, we're noticing a larger and larger reduction in the central density profile. And this reduction seems to be contained to go out to it seems to extend out to the half-light radius. This seems to be a marker for where we're going to see this deviation from the dark matter only profile. And so I'll just skip over these and focus on my conclusions. I've run 12 high-res simulations of isolated dwarf galaxies, all at a 10 to the 10 solar masses. There's good agreement between observation and for a number of observables. And the two main points I wanted to focus on is that there's a strong correlation between early dark matter mass assembly and the stellar mass at z of 0. And namely, the higher concentration, higher Vmax halos are building up more stellar mass and earlier. And also that the stellar mass is correlated well with the density reduction in the centers of these galaxies. And so that there's no modification below 10 to the 6 solar masses, which has been a result that has been seen already, but that once you're beyond that threshold, we begin to see more and more density reduction the more stellar mass there is in these galaxies. And then finally, future work, we want to run these dwarfs in warm dark matter and self-interacting dark matter to see if we can find any differences between what we see here, any observable differences, anything that would really stick out. And this would be including hydrodynamics, and this will be talked about after lunch with James Bullock and Victor Rubles. So that's my talk. Thank you.
Question for Alex before we break? Andre?
Did I understand correctly that you're predicting a large scatter in the stellar mass-halo mass relation at 10 to the 10 solar masses?
At 10 to the 10 solar masses, yes, we're predicting there's roughly 2 orders of magnitude in the spread at this fixed halo mass. I'm not sure if it can really say much about the scatter for other halo masses, but at this very fixed halo mass, there seems to be quite a large scatter in stellar mass for this very particular halo mass. I'm not sure if I can comment on that further.
That's fine. Yeah, follow up?
Well, it seems like previous simulations were showing pretty tight scattering in the 4 kilometers, most including fire simulations. So I just wonder.
Well, I mean, let's go back to.
It's pretty consistent with previous fire simulations. It's about half a decade, 1 sigma, half a decade scatter. So if you plot this on stellar mass, halo mass, it doesn't look crazy compared to previous fire.
Right, you're just seeing a very steep fall off for as we're moving across virial mass. You're seeing a very steep fall off compared to stellar mass.
All right, Andrew, but keep it quick.
Is that level of scatter consistent with the observations? I'm thinking in particular Justin Reed's recent paper where it seems like it gets tighter and tighter as the observations are made better and better.
Right. That is certainly something I haven't compared these two yet, and that would be something I'd have to do in the future. But very good point.
All right, let's thank Alex again.